Hello everyone, my name is Deqing Song from the University of Zurich. Today I'm presenting our work Tactile gesture recognition with built-in joint sensor for cobots. This project was done together with Weimin Yang, Maryam Rezayati, and Professor Hans Wernher Venn at ZHAW. The presentation is separated into 5 sections. First, we will go through our background and motivations of the topic. In the second part, we will model our problem and provide our own methods. In the third part, we'll show the experimental results, and following with section 4 discussion and section 5 of conclusion with our topic. Let's first go into the background and motivations. In human-robot collaboration, tactile perception is becoming increasingly important, especially as we move from Industry 4.0 towards Industry 5.0. Traditionally, tactile recognition heavily relies on external sensors like artificial skins. These systems are expensive, complex, and often require additional hardware installation. So the question we ask is, can we achieve reliable tactile gesture recognition using only the Cobots built-in joint sensors? There are already some work in external sensor-free collision interpretations. The first one is a traditional model-based method, but this one it needs efforts modeling robot dynamics, and it also needs manually tuning each joint's threshold. So then it leads to the data-driven method, using inner parameters as direct input and output directly. Similar methods are used in collision classifications a lot, but less on tactile recognition and interpretations. In this paper, we demonstrated the feasibility of recognizing multiple tactile gestures on a robot solely by using internal joint sensor data, eliminating the need of expensive and complex external tactile sensors. Number 2, we introduced a tactile gesture recognition framework that combines spectrogram-based transformations of internal joint sensor data with CNN-based classifications, effectively bridging the gap between time domain signal processing and image-based deep learning. Number 3, we conduct a comprehensive exploration of signal representations and implement a variety of strategies captures the distinct signal patterns. Number 4, we compare and evaluate the performance of these methods in real time on a Franca Amica research robotic platform, validating their practical applicabilities. Number 5, to ensure the reproducibilities and facilitate future research, we have made our complete dataset open and source code publicly available. Then we move to problem statement and methods. It's easy to model the tactile gesture recognition problem into a multi-channel temporal signal classification problem. The signal include direct parameters from cobots like torque-related parameters and pulse-related parameters and motor-related parameters. We also have some calculated parameters. It's the error-related parameters. We have position errors, velocity errors, and torque error. So our research question is, 1, how to design a tactile gesture recognition algorithm, especially based on convolution neural networks. The second, how different kinds of representations, for example, like spectrogram-based and rod signals, influence the algorithm performance. The third, how different classification algorithm performs and why. In our research, we picked tau external, E derivatives as the 4 features we're using in the feature vectors. The reason why we picked those 4 because we observed significant fluctuations in these 4 features during the content event. We first evaluated simple machine learning baseline like KNN. We also explore RNN-based methods such as LSTMs, which can naturally handle temporal dynamics. And in those methods, we also include majority voting to avoid jittering. For CNN-based methods, we experimented with several types of representations. We have traditional spectrogram representations, which is STFT short-time Fourier transform image, and we also introduced our own short-term transform, which we, in abbreviation, we name it as STT image. And we also have the normal raw-time input as a RT image. And for each representation, we tested both on 2D and 3D CNNs. We also included majority voting to avoid jittering in those CNN-based methods. This is an overview of how each signal type is transformed into 2D or 3D input. The idea is that spectrograms help expose the frequency patterns produced during the tactile interactions, making them easier for CNNs to learn. These are the network architectures we used in our experiment. We deliberately keep them lightweight so that comparison focuses on representation rather than complex model design. Here goes the experimental result. Let me first introduce our experimental setup. The whole system looks like the figure on the left side. There are totally 3 workflows. In the training and testing workflows, we have a digital gloves to provide the true label for a contact event. And in the real-time workflow, we run without a gloves and directly output the model result to a screen display. On the right side, it shows the 3 gestures we picked: single tap, push, and grabs, and the no contact condition in the experiment. Then I will introduce our evaluation matrix. First, we separate all kinds of contact events into 5 classes. The first class is without a contact, the model output 0. That is a true negative. And when there is no contact but the model output is not 0, that is a false positive. We call it a false alarm. If there is a contact, the model output is 0. That is a false negative. We call it a detection failure for the contact. When there is a contact and the model output is correct gesture, then it's a true positive and for both contact and gestures. If there's contact but the model output is a wrong gesture, then it's a true positive for a contact event but it's a false negative for a gesture event. Then we use several matrices in contact detections, which is accuracy, detection failure rate, false alarm rate, detection delay, and recovery delay. We also have some gesture classification matrix, that is accuracy and also detection failure rate. In the experiment, we pick 4 poses during the gear assembling task, and in experiment 1, the test and training procedures happening both on pose 1 to evaluate each model's abilities to classify tactile types in a fixed robot pose, and to eliminating model with extremely poor performance. And then in the second experiment, the training procedure happens on pose 1 to pose 3, and then it's tested on a new position, pose 4. So this one is to evaluate each model's generalization ability and their domain shift with respect to robot pose. This is a table for the both result of experiment 1 and experiment 2. Let's then discuss the result. With the result, we can now answer research question 1 among different types of method, which performs better and why. So we can see here the best of the 2 results is the STFT is 2D CNNs and the STT 3D CNNs. They all reaches above 95% accuracy in gesture classification tasks. If we only look at the contact detection matrix, we can find out the LSTM is already reaching enough good accuracy, that is 94%. But it goes bad on the gesture classification text, which drop under 80% of accuracy for the LSTM. Then for the research question 2, what kind of representation should we pick during the gesture recognition task? Spectrogram-based or raw signal one? With the table of the result, we can see all of the spectrogram-based representation methods is performing better than those with the raw time signal methods. Then comes the research question 3. Do 3D convolution and frequency transformation influence the performance? Let's take a look on the phenomenon 1. We can observe from 2D CNN to 3D CNN, the gesture classification accuracy decrease. But we can also observe the phenomenon 2. In STT 3D CNN, when the convolution structure became more complex, the gesture classification accuracy even increased again back to 95%. In STFT 3D CNN, it's not the same case. When we increase the complexity of the convolution structure of STFT 3D CNN from 7+1 to 4+7, we got a really bad performance and even with a significant cumulative delay. So, in summary, we find out 3D CNN architecture and frequency transform both increase the computational cost of the algorithm. That means when you are picking up the techniques, it's a task-dependent decision. And of course, there are also some limitations of our studies, like generalization limitations, dataset limitations, and methodological limitations. Then the conclusion. To conclude, yes, external sensor-free tactile recognition is feasible. And also, CNNs combined with spectrogram-based representations provide really strong performance on the tasks. If you want to build an effective and robust tactile gesture recognition system, first, the CNN-based model can be considered as possible solutions. Also, spectrogram-based models are better in tactile interpretations. Finally, you need to carefully design the systems based on the task complexity and the computational resource you have. That's all for today's presentations. Thank you for listening. And if you have any concerns or any questions, feel free to contact us via email or via the link through the QR code on the top right. You can also find our GitHub repository, also including our dataset, via the QR code on the bottom right. Thank you again for listening and looking forward to the future connections.